determine the NA. So this NA is not at the middle. Okay, so we have to determine the this is NA. Okay, and the distance from the bottom or the datum equal to y bar, we call it as a y bar. So we have to determine the first one is y bar. So y bar equal to the summation of a y bar divided by the summation of a. So this is the y bar. So this is how to determine the location of y bar. Okay, so in this case, let's say refer to this diagram. We have to divide in three different components. Let's say this is component number 1. So this is component number 2. This is component number 3. So after that, you can use this one. Okay, for the component number 1 plus summation of A y bar for summation A. Okay, for component number 2 and for the component number 3. Okay, so and then after that you can determine the y bar. So once you know where is the y bar or an A, so after this all the distance or location you must refer to the NA. For example, if I want to determine what is the bending stress at point A here, okay, so sigma A here. So sigma A, and this y is YA. So YA is the distance from NA to point A. So this is we call as YA. Okay, if I want to determine the bending stress at point B, so this is the distance of KYB. Okay, or if I want to determine the bending stress at point C, so this is the YC. This is the YC. Okay, that's the YC. So this is how we determine the y bar, and the y bar represent the location of NA, and then NA is our reference. Okay, when we want to determine the bending stress at any point, at the cross section. Okay, so M, Y, and then I. I is what we call as the second moment of area. The I is the second moment of area. This I, it depends on the cross section. Cross section. If we have rectangular or square like this we call as a B or base. D is the depth or height. So I equal to B D cube divided by 12. B D cube divided by 12. Okay. If we have the round like this, okay, so this is the diameter. Okay, I equal to A pi D4 divided by 64 by 64. So this is the second moment of area. Okay, second moment of area. And for the second moment of area, okay, for the shape like this, if we have a shape very simple like this, you just apply the I BD cube divided by 12, or for the circular or round like this, apply the 4 power of 4 divided by 64. But sometimes we have the cross section like this. Okay, so this is cross section. So what we have to do is we divide in 3 components like this. So the total I equal to I1 plus I2 plus I3. Okay, I1, I2, and I3. Yeah? So for example, for the I1, okay, I1, so equal to I bar plus A h squared, A h squared. So I bar in this case for the component number 1 here, okay, for the component number 1, so equal to BD cube divided by 12 plus the area equal to BD, and h squared. So h squared, h is the distance from the centroid to an A. So h is the distance from centroid to an A. So this is the centroid for the component number 1. Okay, this is centroid to an A. So this an A. Okay, so this is H1. Okay, H1. And the same thing for component number 2. Okay, so equal to I bar BD cubed divided by 12 plus AH squared. Okay, so this is what we call as this equation. This equation we call as parallel theorem. Parallel theorem. Okay, this is what we call as parallel theorem. Okay, you should know this one. You should know this one. Normally, the cross section is not square or round like this. So normally it's combination of square or round, or maybe half circle and so on. So it depend on the cross section. Okay. So that is what we discussed before this. We discussed about how to determine the M, how to determine the Y, and how to determine the second moment of area. So now we try to solve a few problems. Okay, I think so. Let me allow your friend to join. Okay, so for this today, we try to solve this problem, this example. Here, this example. So we have a simply supported beam. So simply supported beam like this has a cross-sectional area. So this is cross-sectional area. Okay, so this is we call as I beam. This is what we call as I beam. So determine the bending stress at point B and point C. So this point B, this is point C, and absolute maximum bending stress. Absolute maximum bending stress. Okay, sigma max. Okay, sigma max. So this one is sigma B and sigma C. Sigma B and sigma C. Okay, so this is simply spotted. Let's say this W equal to 10 kilonewton. 10 kilonewton per meter, and L is equal, let's say, 4 meters, for example. So based on this, we have to determine the maximum M. To determine the sigma maximum, we have my divided by I. So M here is M maximum. M maximum. So M maximum in this case occur at the middle because this is uniform diffusion force. Okay, so at the middle. Okay, so you can draw the graph. Okay, to determine the maximum bending in this case. Okay, based on the first method or second method. So let's say from here. We know that D here equal to 20, 20 kilonewton. Okay, here also is 20 kilonewton. Okay, 20, so 20 kilonewton. So you know why here is 20 kilonewton? Why? Why 20 kilonewton? How where 20 kilonewton come from? Can you explain to me why? Why here is 20 kilonewton, please? Hello? Where it's come from? Hello?
Yes, doctor.
Yeah. Why here is 20 kilonewton? Why? Where it's come from?
10 times 4
Uh-huh.
divided by 2
Why divide by 2?
because there
Because there
is
are two
two support.
elements, two sides to
To
support.
support, and this is symmetrical, symmetrical. So it means that support here and support here, they have the same force, same force. Okay, and then after that, you can draw, if you want to draw, let's say shear force and bending moment. Okay, so this is shear force diagram. Okay, V is shear force diagram here is 20, And then here is how much? 10, 20, yeah, 20 here, and this negative 20, yeah, negative 20. Okay, so the graph become like this. Okay, so this is shear force diagram, and then moment diagram. Okay, this is x, this is moment. So this area equal 20. This is 20, yeah. 20 here equal to 20, yeah. Is it correct? Why 20? Why 20 here? Why 20 this area? Is it correct 20? Because this 2, 2, 20 multiplied by 2 is 40. And so this is triangle divided by 2 is 20, 20, yeah. So this is 0. Okay, and then this is 20. Okay, 20, yeah. Okay, and then this is minus 20, yeah. So we have the graph like this, yeah, graph like this. Okay, graph like this, yeah. So the maximum equal to 20. Or in this case, if we have a formula equal to WL squared divided by 8, is it correct? W equal to 10, L equal to 4 squared divided by 8. Is it correct? Equal to 20? Is it correct? Is it
Yes, doctor. Right.
20, yeah? So yes, this is 20, yeah? So 20. Okay, 20 kilonewton. Okay, so this is a maximum, M maximum M, M maximum. Okay, so this is the first thing. The first thing, M equal to 20, equal to 20. Okay, so now we try to determine we have M. So now Y in this case is automatically because this is symmetrical. So this is the NA, so this is NA at the middle. Okay, no problem. Because this is symmetrical, and I. How to determine the I in this case? How to determine I? So let's say in this case you can divide in 3 components. This is component number 1, this is component number 2, and this is component number 3. So component number 1 and component number 3 is the same. Okay, or in this case, you can determine the I based on the second method. You consider this is the whole thing, whole thing. Okay, it's the whole thing. Okay, and then you minus this area. You minus this area. Okay, so if you use this second approach, so I put it here. So I in this case equal to the big square equal to B equal to 220, 220. So this is B, D equal to 150, 150 is 300, and here is 2020 is 340, 340 square, cube, divide by 12, divide by 12. So this is for the whole section, for the whole section. B 250, D is 150, 150, 300 plus 20 is 340. Cube divided by 12, and then minus for this area, So minus, okay, you can put it as B in this case equal to 250 minus 20 equal to 230. Okay, 230. Okay, 250 minus this 20, Okay, this minus 20. Okay, so equal to 230, and D equal to 300. divided by 12. So this is the I. Okay, that is the I. Okay, so this is the second method, or the first method, you just I equal to I1 plus I2 plus I3. Okay, so you can use this one. Okay, you can use this one. I is I1 plus I2 and plus I3. So I1 and I3 is the same in this case. So you can get the same answer. Or you consider this is the whole section. So this is a B, this is a D, cube divided by 12, and then you minus this one, minus this area. So like this, like this. Okay, so that's this. Okay, the unit is millimeter, okay, power of 4. Okay, so that is I. So now we want to determine the bending stress at point B and point C. Point B and point C. Let's say sigma B equal to m bar divided by I. So we have m before this. M equal to 20, 20 kilonewton. Okay, 20 kilonewton. And then Y, okay, Y divided by sorry. Okay, divide by just okay. So I repeat, sigma equal to my divided by I. So m, so we have m before this is 20 kilonewton. Okay, y, it depends on the location of point B, and I, so we discussed before this, I. So here m equal to 20 kilonewton. So y is the distance from NA to point B, NA to point B. So this one equal to 150 millimeter or 0.15, okay, 0.15 divided by this I, I. Okay, so this I. And then for the sigma C, okay, the same formula we have as my divided by I, m equal to 20 kilonewton, y divided by I. So in this case, y equal to what? Y equal to what here? Hello? What is y here? Hello?
It should be 0.
0, 0. Y 0. Y equal to 0, So in this case, sigma C equal to 0, So y 0 because the distance is 0, and this is the neutral axis. The neutral axis is where the bending equal to 0. Okay, no stress, no stress at this location, okay, or at NA, no stress. So that's why we call as neutral axis. Okay, so the same thing if you want to see, to determine, let's say sigma D, sigma D. Okay, we have the same formula, m y divided by I, m equal to 20 kilonewton, and y, this is I. Okay, this I, and this I is the same because it's based on this cross section. Okay, this is cross section. So y here equal to 150 divided by plus 20 equal to 0.17. Okay, so this is the bending stress at point B, point C, and point D. Okay. So, and then the second question is to determine the sigma absolute maximum bending stress. What is, sometimes we ask to determine the maximum bending in compression or in tension. And sometimes we asked to determine the absolute maximum stress. What is different? Okay, what is the difference? So for the maximum, maybe at tension or compression. Compression. So it depends. Okay, compression and tension. Let's say if the beam bend like this to this direction, okay, the top part is sigma C, compression, and the bottom part is sigma tension. Okay, so this is sigma C and sigma T, so tension or compression. But sometimes they ask to determine the absolute maximum stress. What is the absolute? Absolute means that, okay, we just determine the maximum. Okay, no matter is it compression or in tension, it doesn't matter. Okay, you just choose the maximum. Maybe the maximum is compression or maybe the maximum is tension. So that is we call as the absolute maximum bending stress. But if the question asks you to determine the compression or tension, you have to refer to this diagram. Okay, maybe a bend to this direction or maybe bend to this direction. If bend to this direction, okay, the top part is in tension, the bottom part is in compression. Okay, so that is how we can solve this problem. So any question? That's all for this example to determine the I bar to determine the y. Y is in this case very simple because this is symmetrical. So automatically this is the NA. So any question before we move to the second one? Second example. Any question, please? Any question? Hello? Any question?
So far, no question, Doctor.
Okay, no question. So no question, we move to the second one. Next one. Okay, so this is also the I-beam. So this is also I-beam. So we have two different design in this case. Two considerations have been proposed for the design of a beam. So this is I-beam. So it looks similar. Okay, it looks similar. Okay, determine which one is support a moment of 150 kilonewton with the least amount of the bending stress. What is the stress and by what percentage it is more effective? So in this case, we have two different design for the beam, and the beam is we have the moment 150 kilonewton to apply to this beam. So which one can support more moment? Okay, compare A and B. Which one is more effective? Which one? Okay, based on this diagram, you can guess which one, A or B, is more effective. Which one? Hello? Could you guess which one is more effective? Design A or design B? And then we can prove later on. Design A, why?
A.
What is your justification? Why?
Because I think for design B, we can see that there is more weight
Huh?
used on a smaller board, so
Uh-huh.
it might not handle the stress well. The
Uh-huh.
other one is less stress on two bars, so
Yeah,
better management of stress.
yeah. Is it correct? So for you, design A is better compared to B.
Yes, doctor.
Yeah. Any suggestion? Which one is more effective, A or B? And justification why? Why you choose A or B? Why? Okay. So in this case, let's say you can see that from this is I-beam. So this I-beam, so the top part and the bottom part, we call this is as the flange. Flange, we call as flange. And this one at the middle, this is what is this? We call what? This one? This is what is this? What is this? What is component we call? This is wet. This is wet. So the top and the bottom here we call as a flange. Okay, this is a flange, and at the middle here we call as a web. Okay, that's the term we use for I-beam. I-beam. Okay, for the first design, so we double the web. So you can see that we double the web. Okay, and for design B, we double the flange. So which one is better? Okay, which one is better? I just to show you. You can see what I showed to you. You can see this one. You can see. Hello, you can see. Because I want to explain to you based on this one. You can see this one. Why
Yes,
this
doctor.
object? Okay. Let's say the same object. The same object. Okay, this is same object. Okay. If I put the orientation is like this, orientation like this. This is the first one. Compared to this second one. Okay, this is the first orientation. This is the second orientation. The same object, but the orientation is different. Okay, this one, the first orientation, and this is the second orientation. And I apply the force to this object. Okay, I apply the force to this object. If the orientation like this is the force I apply here. If the orientation is like this is the force. Okay, which orientation is stronger? Is it orientation number 1 or orientation number 2? You have the answer. Is it orientation number 1 or orientation number 2, please? You understand what I try to explain to you? Hello?
No, no, understand, doctor.
Huh? You understand or not? You not
No,
understand?
no.
Okay, let's say this is the object. This is the beam. This is the beam. This is our beam. Okay, so I just to show you here is the difference if we change the orientation. The orientation, the first orientation become like this. Okay, let's say this is the beam, and then I apply the force at the middle. Okay, that is the first orientation. The second orientation, this is the second orientation, like this, and I apply the force at the middle. Which one is stronger? Is it the orientation 1 or orientation number 2?
1.
1 or 2? You can see that.
One.
Okay. This is, let's say this is the cantilever beam. This is cantilever beam. Orientation number 1 like this. And I apply the force here. And this body will bend. I think I use this one. It's better. The first orientation like this. And I apply the force. So this beam will easily bend. Easily bend. Compared to the second orientation is like this, and you apply the force to this direction. Is it the second one is easily bent or not?
No, doctor.
No. So which
Second
one
so
is
easy.
better? Which orientation is better? Is it this orientation
Second.
or this orientation? Second one,
Second, second.
Yeah. Second one is more, can carry more load compared to this first one. So based on that, so this first design and the second design, of course, this one is better compared to this one. Okay. We can prove this one. We can prove this one. Just based on the formula that we have. Sigma equal to my divided by I. So M here, so this, let's say for the A, okay, design A, M equal to same 150 kilonewton, okay, and then Y divided by I. So Y in this case, so because this is symmetrical, this is the NA, so this is the NA. Okay, the same thing here, this is the NA. Okay, same location. So for the maximum, okay, occur when Y is the maximum. Y maximum is from NA to here. This is Y maximum. So in this case, equal to 300 divided by 150 plus 15,165, 0.165. Okay, 0.165. And I you can calculate the I. As I mentioned to you, this is because it's symmetrical. You can consider this is the whole section. Okay, this is the whole section. Okay, so I in this case equal to B equal to 200, D equal to 300, 330, okay, 330, 300, 15, 15, so cube divided by 12, and minus this one, okay, minus this one, equal to B, okay, 200 minus 30 equal to 170. Okay, so this BD equal to 300, equal to 300 cube divided by 12. So this is I. Okay, so this I. Okay, you can put it I here. Okay, and then you know megapascal. Okay, so this is design A. And for design B, the same thing. Okay, so we have a my divided by I. Okay, my divided by I, so sigma m equal to same 150 kilonewton. Okay, y and I. Y in this case from NA to the top or bottom. Okay, the bigger Y or highest Y. So this Y. Okay, this one equal to 150 plus 30 equal to 180, 0.18, 0.18. Okay, and I is for this one is I for the whole section. This one I equal to B 200, D equal to 360 cube divided by 12. Okay, minus this area. Okay, this area. So B equal to 200 minus 15. 200 minus 15 equal to 185. 185. Is it correct? 185. This is B. D equal to 150. Sorry, D equal to 300. Cube divided by 12. Okay, so this is I. Okay. And then you can calculate. You can compare this one and this one. Which one is the stress is smaller or smaller? Smaller. Which one is smaller? Of course, in this case, again, the smaller is this one. Okay. Okay, design B. You can check. You can check. Okay, sigma for design B is smaller compared to design A. Okay, why? Because the orientation, you can see that the orientation, the design, okay, design of this beam, okay, the logic is based on what I explained to you before this. Okay, so in this case, when the height is bigger, so you have I is higher. When I is higher, okay, you divide by the bigger I, so that's why you can get the smaller sigma. Okay, so in this case, the design B is better compared to design A. Okay, you can prove, you can prove this one based on this calculation. Okay, so I already showed it to you. So I hope you can complete this solution, this calculation, and then you can get the answer. Okay, in this case, sigma for the B is less than sigma A. Okay, this is design B, this is design A. Okay, because of the orientation, because this orientation. Okay, so that is for the bending stress. Okay, so that's why in the in this example, okay, so it's very clear for us to understand. Okay, what is the best orientation when we design the beam? Okay, when design the beam, is it orientation is to be like this or like this? The same beam, but the orientation is different. So it gives the different result. So you have to know this one. Okay. Any more question before we go to the this one actually to determine the moment. What is the moment here? Okay, what is the moment? Okay, to determine the maximum stress. Okay, okay, we want to the maximum stress here is 100 megapascal. So what is the moment? So again, sigma equal to my divided by I. So the sigma here is 100 megapascal. So M, this is Y, and I. So you want to determine the M. What is M? Okay, before we determine the M, so based on this cross section, this is cross section for the beam, we can determine the Y. Okay, Y is the location, is based on the location of an A. So location of an A, and I is based on the cross section. So this is more looks very quite complex because we have 1, 2, 3, 4 components in this case. So, but I think it's okay. You just draw like this. So draw like this. Okay, you draw like this. Okay, this is cross section. You just name it as this is cross section number 1. This is the number 2. This is number 3, and this is number 4. Okay, and then you just apply the Y equal to Y bar equal to summation of A Y bar divided by the summation of A for each section, and then after that you know the Y bar, and let's say this is the datum. You choose that this is the datum or reference, and then maybe here is the NA. Okay, so this is Y bar. Okay, so Y bar maybe at the top part or bottom part. It doesn't matter. It depends on the this calculation. Okay, so this is the first thing that you have to solve first before you go to this formula. So you have to know this one, and then the second thing is about the I. I in this case equal to I1 plus I2 plus I3 and plus I4. Okay, you have to know. You must apply what we call a parallel theorem in this case, and then I2 and I3 is the same. So this I3 or this one equal to 2I. Okay, 2I1 or 2I2 or 2I3 doesn't matter. So because it's the same, the same. So this is I. Okay, for example, in this case, let's say if I want to determine the I1, okay, I1 equal to I bar plus AH squared. So I bar for the component number 1 equal to B, so this is B, so this is D, okay, B D cubed divided by 12. 12 plus A is the area, so BD, and H is the distance from centroid to NA. So this is the centroid of component number 1 to NA, So this is, let's say, we call as H1. So this is H1. Okay, N squared. Okay, so this is component number 1. Component number 2 is the same. You have to apply this formula that we call as parallel theorem for component number 2 and number 3, and also for component number 4. So that is for the total I. Okay. So after that, let's say if I want to determine what is the bending stress at point D, for example. Okay, at point D. So Y is this case, okay, is the distance from point D to NA. Okay, this is YD. So this one, Y. Okay, we measure from that point to NA, okay, to NA. So that is the Y. And I is based on the cross section. Okay, so I think that's all how to solve this problem. So I hope you try yourself how to solve this problem. And if you have any problem, let me know. Let me know. Yeah, I try my best to help you, to explain to you. And then, as I mentioned to you, for the test two, later on, the first question is come from to how to draw shear force and bending moment diagram. And the second question is come from this part, how to determine the bending stress. Okay, how to determine bending stress. So I think that's all. And then I already shared the result of the test one. Okay, so I don't know whether you happy or not, but in overall, for the overall, so that is the average. That is the average. Okay, some of you still have the problem to understand the free body diagram, how to solve the force analysis and so on. So I hope you improve that one. Okay, because later on maybe our calculation is more complex. If you not understand for the basic things like how to determine the moment, how to draw the free body diagram and force analysis, you are in trouble. So please make sure you understand the basic thing before we discuss the complex problem and so on. So I think that's all for today. So if you have any question, please. You have any question, please? You have any question before we end the session?
Doctor,
Yes.
when is test 2?
What? Pardon?
When is test 2?
Test to when? I don't know.
Yeah.
I think so. Academic office will share later on. But normally before end of this semester, normally before I think 3 or 2 weeks before end of this semester, normally. Okay.
Okay, thank you, doctor.
And then for the test 2, we cover until chapter 7. Yeah, so question number 3 is come from chapter 7 later on. It's about the shear stress. So this is a bending stress. And later on for the chapter 7 is about the shear stress. So that is question number 3. Okay, so I hope you try yourself to solve the question. You try your best to understand this one. So this is beam is very, very important for us, for the mechanical engineers. So for you to understand, because normally our problems, our design, our component is related to the beam. Maybe the orientation or design is different, but we can use that approach or that method how to analyze the component. Okay, so I think that's all. Thank you very much for your attention. So see you next week on Sunday.
Thank
Okay,
you,
bye.
Doctor.
Okay, bye.
Thank you, doctor.
Okay,
Stay safe,
welcome.
Doctor.
Thank
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 you.
you, doctor.
Okay, welcome.
you, doctor.
Thank you, brother.
Okay.